Gloria, are you able to see my screen? My whiteboard projection?
Yes, sir.
Okay, good. Yeah. So analytic and harmonic functions. So the beauty with this chapter is that the things we are going to discuss on are directly related to what you discussed in differential calculus. So majorly we are going to review, or the concepts are directly related to concept of differentiation in calculus. So once we give the definition of what we mean by analytic, what we mean by harmonic, the rest of the stuff will be simply to do the differentiation of complex valued functions, which actually turns out to be the same way we deal with real valued functions. So nothing much to be scared of. So so today is 22nd. So I hope what I'm writing you can see from end. Is that in order that what I'm writing on the whiteboard is visible from end? Please participate so that actually I know if there's a problem or not. Are you able to see what I'm writing? Okay, good. Yeah. So we started by defining what we mean by an analytic function. So a function W equals to f of z, which can be given by u of x, y plus iv of xy, is said to be analytic. At a point z naught, which is in the domain of the function f, if it is differentiable at z naught and in the neighborhood of z naught. So function w given by f of z, which is the same as u plus iv, is said to be analytic at a point z naught if this function is differentiable at this point z naught and in the neighborhood or points around the point z naught. So your function f of z is differentiable at z naught. We mean that the function, the derivative of the function exists at that point z naught or near or points around the same point and the points around z naught. So the terms regular and holomorphic are also used to define or to mean analytic. So we are saying that when we say analytic, in the same way of saying regular, in the same way of saying holomorphic. So these are the synonyms which can be used interchangeably, refer to the same thing. A function being differentiable at a point z0 means the function is differentiable at that point and in the neighborhood of the same point. So we say that a function f of z is analytic in a domain if it is analytic at every point of that domain. That simply means that the function is differentiable at every point of the defined domain. So in simple terms, saying f of z is analytic in a domain simply means f of z is differentiable at every point of the domain. Now the point where the function is not differentiable is called a singular point of the function. A function which is analytic everywhere this to mean for all z in the complex plane is known as an entire function. So examples, all polynomials are entire functions because they are differentiable everywhere. And then some of these results from calculus are obvious. That one, analytic function is always differentiable and continuous. But the converse is not true. And then analytic function is always continuous. And also converse is not true. And we can also say an entire function is always analytic differentiable and continuous but the converse is not true. So let's state and prove the necessary condition for function f of z to be analytic. The necessary condition the necessary condition for or conditions for f of z to be analytic. So we give the statement and then the necessary conditions for a function w equals to f of z equals to u plus iv to be analytic at all points in a region R, R1 partial u partial x is equal to partial v partial y and then 2 partial u partial y is minus partial v partial x, provided that this partial derivatives exists. Provided that partial u partial x, partial u partial y, partial v partial x, and partial v partial y exists. So let me know when you are ready so that we can provide the proof. Can we proceed? Okay, good. So proof. Let W equals to f of z be the same as u plus iv be differentiable functions, be differentiable or simply analytic function in a region R where u and v are functions of x and y. So I mean, u depends on x and y, and v also depends on x and y. So I have a function w u plus iv, or f of z equals to u plus iv. Then both u and v are taken as functions of both x and y. Also, let delta u and delta v be small increments, or some can call it changes, of u and v respectively, corresponding to the increments or changes delta x and delta y of x and y. So here we mean delta u is change in u, or small change in u, or increment in u. Delta v is a small increment or change in v. Delta x is small change in x or increment in x. And delta y, small change or increment in the variable y. So then now we can write. So therefore, f of z plus delta z, z plus small change in z, will be given by u plus delta u plus I times v plus delta v. So that should make sense from the structure of f of z. F of z is given by u plus v, iv. So when I introduce a small change in z, then I'll have both a small change in u and a small change in v. Now, if I take f of z plus small change in z, I subtract f of z divided by small change in z, this is the same as taking u plus delta u plus I times V plus delta V then minus, what is the value of f of z? What is the value of f of z from definition? What is f of z from definition?
U plus IV.
Correct. U plus IV. U plus IV. And then divided by delta z. So that's just by definition, replacing the value in the formula as per the definition of f of z and f of z plus delta z. Then that's the same way we were defining this difference quotient when we were doing differential calculus. We have this u plus delta u plus iv plus I delta v minus u minus iv, opening brackets, divided by delta z. That's just defining that difference quotient. Some terms will cancel out in the numerator. Which term and which term? IV, IV, IV. The other terms? U and U, okay? U and minus U. So therefore, this will give us just delta U plus I delta V divided by delta Z. So this is the difference quotient. So if we define limit as delta Z approaches 0 of this difference quotient, f of z plus delta z minus f of z divided by delta z will be the same as limit as delta z approaches 0 of delta u plus I delta v divided by delta z. So just as given the previous step, that's the definition of that difference quotient. So which you can write it as limit as delta z approaches 0 of delta u over delta z plus I delta v over delta z. Hope that will make sense.
Yes.
Yeah. So that's by just definition.
Yes.
So now once you have defined that different limit of that difference quotient, you remember that delta z can approach 0 from any direction on the complex plane. So since delta z can approach 0, along any path in the complex plane, we can consider two cases. Case one, along the real axis. So I hope you remember that this is what we mean by complex plane. So this is what we call the imaginary axis. And then this is the real axis. So this vertical axis is the imaginary axis, and then this way you have 0. So when we approach 0 along this axis, and don't forget that z as a complex number is always given by x plus iy or yi. So on the real axis, what is the value of y? On the real axis, y is actually just the same way we interpret the normal Cartesian plane, even if you are dealing with real numbers. If you draw the xy axis, what are the values of y on the x-axis? If you are moving along the x-axis, what is the y value?
Zero.
0. So on the real axis, y is 0. So this implies z is the same as x plus I times 0, which simply means z is the same as x. So if you are on the real axis, z is just the same as x. So therefore, delta z will just be the same as delta x. The change in z will just be congruent or equivalent to the change in x because the values of y on the real axis are 0. So probably maybe call this equation 1, or this expression for the limit as delta z approaches 0 of the difference quotient, call it equation 1. So using this value in equation 1, we have that the limit as delta z approaches 0 of delta u over delta z plus I delta v delta z will be given by limit. So instead of delta z, we replace by delta x. So delta x approaching 0 of delta u over delta x plus I delta v over delta x. So what we're simply doing is to replace delta z by delta x because of the relationship we have obtained from this point. Maybe call this one 2. Delta z is the same as delta x on the real axis. And from your differential calculus class, you know that when you have a limit of sum of two functions, is the same as limit of sum of two functions is the same as if I have limit of f plus g reduces to from properties of limit. This we did the other day. So delta u, delta x plus I limit delta x of delta v over delta x. And if you remember what you did in differential calculus, if I have this limit from calculus, we know that limit as small change in x approaches 0 of delta f delta x is nothing but derivative of f with respect to x. This is a result from calculus. But now, because we are dealing with u is a function of x and y, and v is also a function of x and y, we have the same interpretation, but then the derivative here is now becomes partial, not now the ordinary derivative. So this will be the same as, this will be partial u, partial x plus I partial v partial x. And this is the same as just saying derivative of the function f. So that is how we obtain the first relation. That so the limit as delta x approaches 0 of delta u over delta x is nothing but partial u partial x. Limit as delta x approaches 0 of partial v partial x is nothing but partial v partial x, borrowing from this result in calculus. And this is actually the partial derivative of the function f. So call it 3. And because actually they remember from the start, when you say the limit as delta z approaches 0 of f of z plus delta z minus f of z divided by f of z is just the definition of the derivative of the function f of z. But this one here, if you recall, when we introduced the concept of derivatives, this expression here is nothing but the definition of the derivative of the function f of z. So that's why you're saying that f prime of z reduces to partial u partial x plus I partial v partial x using this result at this point here. And then case 2, let's see what happens along the imaginary axis. So I can sketch, this is the real axis. This is the usual imaginary axis. This way I have 0. Don't forget that always z is given by x plus iy. So if I'm moving along this axis, either down or up, but along the imaginary axis, and I want to approach the point 0, what is a common trend about all values on the imaginary axis? what happens to x and what happens to y on the y-axis, on the imaginary axis? X? Come again? On the imaginary axis? Unmute and say the answer. X is always 0 on the imaginary axis, correct? So x is 0 on the imaginary axis. So which means then z is the same as just 0 plus iy, which means z is the same as iy. So then partial delta z will be the same as I delta y. So then now, from equation 1, I remember equation 1 was, I remember that this is the definition of the f prime of z. So f prime of z will be equals to limit as delta z approaches 0 of delta u over delta z plus I delta v over delta z. This will be limit. Now, where there's delta z, we put delta I delta z approaching 0 of delta u, where there's delta z, you put I delta y plus I delta v, I delta y. I'm simply replacing where there's delta z by I delta y. Now, what is the, if I don't want to have, so remember this I and I cancels out in this second part. But then what is the simplification of delta u over I delta y? If I don't want an I in the denominator, what should I do to that fraction? What should I do to the fraction delta u over I delta y if I don't want an I in the denominator? Okay, so like I'm asking you, if I have 2 divided by I, how do I remove the I in the denominator? How do I remove I in the denominator? Okay, maybe that's a hard question. Maybe that's a hard question. If I have 2 over 3 plus I, How do I simplify this? How do I simplify the complex number 2 over 3 plus I? Yes, we multiply both the numerator and denominator by the conjugate of the denominator. So what is the conjugate of I? So what is the conjugate of I? So negative I, correct. So therefore now we multiply both the numerator and denominator by negative I. So negative I, negative I. So negative I by I gives? What is negative I times I? Negative I by I? I by negative I gives? Okay. Okay, what is I times I? I by I? I squared. So negative I squared. But what is the value of I squared? Negative 1. So negative 1 gives 1. So denominator will be 1. And then the numerator will be negative I delta U. Okay? So therefore, this is the same thing as writing the derivative of f of z is limit as I delta y approaches 0 of negative I delta U divided by delta y plus delta v over delta y. Then since y is change in y is the only thing that is being affected by the limit, so this is the same thing as just saying limit as delta y approaches 0 of negative I delta U delta y plus delta v delta y. So that this can be written as limit as delta y approaches 0 of negative I delta U delta y plus limit delta y approaches 0 of delta v delta y. Remember, the limit is affected by change in y, so negative I can as well be factored out of the limit. So that you have negative I limit as delta y approaches 0 of delta U over delta y plus limit as delta y approaches 0 of delta v over delta y. So what is the meaning of this limit? So what is the meaning of the limit in pink brackets? If you just follow the same concept we used in the case 1, that limit defines what? What is going to be the limit in the pink brackets? Or the limit? What does this limit imply? This is the derivative of which function with respect to what?
With respect to partial x.
Yeah, so x is not here. So this is negative I partial u partial y plus this one. Partial v partial y. So give this one question 4. So call this one 4. So you see equation 3 we had f prime of z is given by, can you read for me the result of equation 3?
Partial u over partial x
Plus
plus I
partial x, correct. So this was equation 3. And then here, equation 4, we are saying f prime of z is given by partial v partial y minus I partial u partial y. This is what we have as our equation 4. So what can you say about equation 4 and equation 3? What can you say about equation 3 and equation 4? That one you don't require to reason. You just use your eyes. Question 3 and question 4. What can you say? You just use your eyes and tell me what observation can you make out of question 3 and question 4? What can you say in 3 and 4? No? Don't complicate it. Just what you can see from what is giving the result in 3 and what is giving the result in 4. without going into jargons. Just use your eyes. The obvious thing that even someone who is not in this class, when you show them 3 and 4, they will tell you. Okay, that we're becoming a lawyer. So just we don't want lawyers. The obvious thing that what you see in 3 and 4. I can't hear. And you see that the 3 and 4 are just defining the same thing. Don't you see that 3 is just derivative of f of z and similar to 4? So both 3 and 4 are just defining the derivative of the function f. So we can always now equate them. So equation 3 is the same as just equation 4, because all these are defining the derivative of f. So here we have partial u, partial x, plus I, partial v, partial y, equals to partial v, partial y, minus I, partial u, partial y. And when do we say, remember these are left-hand side is a complex function, similarly right-hand side is a complex function. Or even if you view them as complex numbers, when do we say that two complex numbers are equal? For this equality to make sense. What must be the condition for these two for this equal sign to make sense? It's like I'm asking you, if I have two complex numbers, a plus bi is equals to c plus di, what is the condition for this to be a true equality? If a plus bi equals to c plus di, then what will a? Correct, and b equals to d. So that's the condition that assures the equality to make sense. So here then it means that partial u, partial x must be equals to yes, partial v, partial y. And then partial v, I remember this is x. This is x. This is x from actual equation 3. So what would be partial v, partial x? Or if you want, if you like, if I want to have uniformity so that on the left-hand side, I just have u values. What is partial u, partial u, partial y? Correct, negative partial v, partial x. I hope people are able to see where negative is coming from. And then we are done. So this is the end of proof. So this relationship, the equations partial u partial x equals to partial v partial y and partial u partial y equals to negative partial v partial x are collectively called the Cauchy-Riemann equations. What we normally abbreviate them as CREs. So these are what we call the CREs. So CRE means Cauchy-Riemann equations. Cauchy-Riemann's equations. So if a function satisfies the Cauchy-Riemann's equations, then such a function. If a function satisfies the Cauchy-Riemann's equations, then such a function is called an analytic function. So I'll state the theorem without proof. You can check it in the textbook. So there's what we call sufficient condition for f of z. Remember, the CREs are necessary conditions for f of z to be analytic, but is not a sufficient condition for f of z to be analytic. So to have for f of z to be analytic sufficiently, then we need to add another condition that the CREs must exist and also all the partial derivatives. So the sufficient condition for function f of z to be, which is equals to u plus iv, to be analytic, at all points in a region R, so the first two conditions is that the CREs must be satisfied, that partial u partial x, the same as partial v partial y, and partial u partial y should be negative partial v partial x. And then the second condition is that partial u partial x, partial u partial y, partial v partial x, and partial v partial y must be continuous in the region R. So the continuous functions of x and y in R. So you can get the proof from the textbook. So I give a 9 minutes break. So we continue at 3:30.